Hi everyone, it's the Math Sorcerer here with Chegg. In this video, we're going to discuss indeterminate forms and L'Hopital's rule. Let's start doing examples. So our first example is the limit of the natural log of x over x as x approaches infinity. Let's go ahead and work through this very carefully. Solution. So the idea is that when x is approaching infinity, the numerator is also approaching infinity, and the denominator is also approaching infinity. You have the form infinity over infinity. So whenever you have infinity over infinity, or negative infinity over negative infinity, or 0 over 0, or even infinity over negative infinity, or even negative infinity over infinity, so any of these forms, what you can do is you can apply L'Hopital's rule, which basically says that you write the limit again, the limit as x goes to infinity. And because we have infinity over infinity, basically you just take the derivative of each piece. So the derivative of ln x is 1 over x over, and then the derivative of x is 1. By the way, all of these are called indeterminate forms. There are other indeterminate forms, but it has to be these in order for L'Hopital's rule to work. This is equal to the limit as x approaches infinity, and 1 over x over 1 is just 1 over x. And at this point, it becomes very clear, as x gets really big, 1 over x gets really small, and so the limit is equal to 0. The answer in this case is 0. Let's do another one. Part B, we have the limit of x squared over e to the x as x approaches infinity. Let's work this one out. Solution. So again, as x gets really big, the numerator also gets really big. So it's approaching infinity. Same thing on the bottom. E to the x is approaching infinity as x approaches infinity. So again, we have infinity over infinity. We can apply the powerful L'Hopital's rule. We have the limit as x approaches infinity. So we just differentiate. The derivative of x squared is 2x. And the derivative of e to the x is e to the x. And so again, we have infinity over infinity. We can apply L'Hopital's rule again. So this is the limit as x approaches infinity. The derivative of 2x is 2. And the derivative of e to the x is just e to the x. And at this point, you can clearly see, because we have a constant in the numerator and x is approaching infinity, e to the x gets really big. So this fraction gets really small, and so the answer again is 0. Very powerful rule, and I just want to emphasize that you have to make sure that it has one of these forms. We'll do an example soon where it's not going to have one of these forms, and we'll have to do some math to make it fit one of those forms. Anyways, for now, let's do another one. This time we have the limit of sine 2x over 3x as x approaches 0. So if we plug in 0 here, we'll get the sine of 2 times 0, so the sine of 0, over the sine of 3 times 0, which is the sine of 0. Sine of 0 is 0, so you get 0 over 0, and that's one of the allowed forms for L'Hopital's rule. We can actually use it in this problem to make it easier. Solution. So this is the limit as x approaches 0. So the derivative of sine is cosine, but here we have the sine of 2x. We have an inside function, so we have to use the chain rule. We take the derivative of the outside, so we get cosine of 2x. We leave it evaluated at the inside, and then times the derivative of the inside function, which is just 2, over, same thing on the bottom, the derivative of sine is cosine. Leave the inside untouched. And then times the derivative of the inside, which is 3, right? Chain rule. You take the derivative of the outside, evaluate it at the inside so you don't touch the inside function, then you multiply by the derivative of the inside function. By the way, the reason it's 2 is because the derivative of x is 1. Same thing for 3. Now we can actually plug in 0 and drop the limit sign. So this is the cosine of 2 times 0, so cosine of 0 times 2, over the cosine of 3 times 0, so cosine of 0 times 3. The cosine of 0 is 1, so we get 1 times 2 over 1 times 3, and so we get 2 over 3 as our answer in this problem. All right, let's go ahead and do one that's a little bit harder. So in this last example, we have the limit as x approaches infinity of x to the 1 over x. So if you think about it, as x approaches infinity, you're going to get infinity. And then as x approaches infinity, 1 over x approaches 0. So this has the form infinity to the 0. That's actually an indeterminate form, but not one that allows us to use L'Hopital's right away. There's actually a technique you can use. And you know to use this technique in these problems whenever you have like a variable to a variable. Like if you had 1 plus x to the 2 over x, this technique would also work, etc. So variable to a variable power, typically this is a good technique. So the first step in this technique is you let y be equal to x to the 1 over x. Okay, that's the first step. The second step is you take the natural log of y. So ln of y equals ln of x to the 1 over x. And then you just go from there. So in this case, basically, because we have 1 over x as an exponent, we can bring it down using the power rule for logs. So this is ln y equals 1 over x, ln x. So again, step 1, you take your function, which in this case was x to the 1 over x, you call it y. And then you get rid of the exponent by taking the natural log and bringing down the exponent. Now you take the limit of this. So we have the limit as x approaches infinity of the natural log of y. That's equal to the limit as x approaches infinity of ln x over x. And now we are in a very beautiful place because as x approaches infinity, so does the natural log of x. So this has the form infinity over then infinity because x also approaches infinity. So that means we can use L'Hopital's rule. In fact, I'm going to indicate it by drawing an arrow and writing LH, just to be really clear. So we're using L'Hopital's in this step. So this is the limit as x approaches infinity. And then the derivative of ln x is 1 over x. The derivative of x is 1. This is the limit as x approaches infinity of 1 over x, which is 0. And so now we have to be careful. This is the step where I think a lot of people don't understand how to get the answer after this step. So let me just show you. So what did we do? We showed that the limit of ln y as x approaches infinity is equal to 0. So written another way, we showed that the natural log of y approaches 0 as x approaches infinity. But we're concerned with what happens to y, right? Remember, we called our function y at the beginning. Our original function is y equals x to the 1 over x. We'd like to retrieve y from this. What we can do is we can exponentiate. So here we get y approaches 1 as x approaches infinity. But what's y? Y is x to the 1 over x. So we've basically shown that the limit as x approaches infinity of x to the 1 over x is equal to 1. And so the answer is 1. So just a quick recap to make sure you got it, because this is a much harder problem. Step 1 is know when to do this. Basically, if you have a variable to a variable power and you have an indeterminate form like this or something else, this might be a good idea. You start by calling your function y and then taking the natural log of both sides and eliminating that exponent that's problematic. Then you take the limit and usually use L'Hopital's in this step and you get an answer. Get the final answer, just think about what's happening. We have the natural log of y approaching 0. That means e to the ln y approaches e to the 0. That means y approaches 1. But what's y? It's our original problem. So basically you can just exponentiate, get back your original function every single time. Kind of a fun problem. I hope you've learned something in this video, and if you enjoyed this video, make sure to check out more videos on Chegg. Good luck.